going to use this video time to introduce exponential relations. They follow the equation pattern y equals ab to the x. Probably have seen this type before, so I just want to review some of the parts of this equation that are important. So a is what's called the initial value. It could also be called the y-intercept as well, because whenever x equals 0, we have a power of 0 on the b, and so what we're left with there is a times 1, which is a. So a is the y-intercept for that reason, also called the initial value. B is the growth or decay factor, and the exponential relation will exhibit growth if b is more than 1, and it will exhibit decay if b is between 0 and 1. I'll just show a couple of examples in the graphing calculator to illustrate those two types. Okay, the first one, I'm going to put in a as 2. My base is 1.3, and let's use a simple exponent of x. So this should involve exponential growth because my base is repeated multiplication of the number 1.3. So let's have a look. When we first set up for the graph here, if you're not sure what the window settings should be, try zoom 6. Zoom number 6 is going to give you the standard viewing window, which gives you negative 10 to positive 10 in both directions. I can clearly see my graph well framed there. I'm going a little bit closer with zoom 4, which is called the decimal zoom, and that gives you a tenth or decimal value when you trace along. You'll see as soon as I press trace, I can move along the graph at a tenth of a unit. So there I'm seeing my initial value right at x equals 0, y equals 2, which is my a value. And I can see with a base of 1.3, the curve definitely climbs, so it's growing, but not really aggressively. If I was to change my base to 3, I would find that if I was to go back to the graph, it would rise much more quick. Okay, next example here, I'll choose a different initial value. I'll use 3.5. I'm going to use a base of 0.5, which fits the 0 to 1 range, and I'll use just x as the exponent. So now when I'm going to graph this one, I'll start with zoom 6, the standard viewing window. Let's have a look. Okay, sure enough, it falls to the right and it's nonlinear, so this is exponential decay. Okay, in example 1, we can use a multiplier of 1 plus the growth rate, which would be 1.0125. In this case, starts at 9.3 as an initial value. That would be the population of Ontario in 1985, and T is years after 1985. So we're trying to solve this, which year did Ontario's population first exceed 10 million? Okay, so that's the equation we're trying to solve. So this is an application. Okay, so what I would do is I would either try a systematic trial, or here I'll use graphing technology. Okay, so here the strategy is use the left side and the right side of the equation as y-x relations. Y equals 10 is a horizontal line. Graph my exponential growth curve there as y1. Let's have a look. I'll start out with the standard viewing window. Okay, here comes in the just very gently growing population curve. Cutting across soon will be the 10 million population value. You can see here that my solution is really close to the top, so I'm just going to step in and bump up the y max to something a little bit more than 10, and then I can regraph, and at that point I should be able to see the point of intersection on my graph, so I could come in at that point and I could either readjust the window, or I can just apply the second trace, option number 5. Where we're on the curve isn't important, but the first curve is shown in the top left hand corner. That's my growth curve. Then it asks for the second curve, which is the population 10 value. Enter, guess, move over to the point of intersection, which I think is over in quadrant 1 somewhere, and I'll calculate the rest of it. So it gives 5.84 as an x value, so that would be 5.84 years after 1985 would be when 10 million population is reached. So it would certainly exceed that probably in 1991, which would be 6 years after 1985. Okay, example 3 is an application involving a half-life. So with caffeine, it would be an example. It has a half-life of about 5 hours. So if you drink caffeine and it stays in your system, after 5 hours, half of the caffeine has been broken down or metabolized. Another 5 hours, half of what was left before would be gone, and so on. Okay, so in this case, we start with 200 milligrams, 5-hour half-life. How long until you have 10 milligrams of caffeine in your bloodstream? So we have the decay equation above for things that break down or reduce. The first initial value is what we start with. We're going to, of course, use half as our multiplier, or our base, rather. H is the half-life value, which is for caffeine, what we're told 5 hours, and T is the time. So we solve this problem by just setting the amount equal to 10, with the initial value equal to 200, and the half-life equal to 5. Okay, to solve this, I just write what I know, set up the formula, substitute what I know into the formula, and then in this case here, I'm going to just simplify this a little bit, and I arrive at 10 over 200 is 0.05, which would be equal to 0.5 to the t over 5. Now here, instead of using a graphical approach, I'll try systematic trial. Okay, I'm going to try a few values here to show the results. I used t equals 10, 15, and then I jumped up to 30. I saw that raising 0.5 on the right side to fractions divided by 5, I had to get up to 30 over 5 before I got down small and nice. A couple more values between 15 and 30. Hopping along by 5 here, I see that t equals 20 is a little bit too high. T equals 25 is a little bit too low, so I'm getting closer. Okay, added a couple more values, and we can see that we're focusing in on 0.05 after 21.6 minutes. It is equal to 0.05, so 21.7 minutes, and it should be just a little bit below that level. Okay, the other type of curve is the exponential growth with doubling, and that uses a similar form where instead of how long it takes to cut in half, it's how long it takes to double. So d value is the doubling period. A sub 0 is still your initial value after time t, and a on the left side is the amount. So we can use that type of an equation to model things that grow, such as the population of Ontario. We can go back to that problem now and just revisit it with trying to determine the doubling life, or doubling time. So here I'm trying to solve for the doubling time. So I'm just going to double 9.3 as an initial population. 18.6 is the population value. Divide both sides by 9.3, and now I get my power 1.0125 to the exponent t. Simplify, and I got 2 equals 1.0125 to the t, which I'll solve using graphing technology. I'll pull up my graphing calculator here, and I've got the right side as y1 and the left side is 2. I've set my window so that somewhere between in the y direction, let's say -1 and 3, I see the value 2, going up by a half at a time. I don't know how long it's going to take to double, so let's allow up to 100 years after 1985, and I'll increase by 5. And then we look at the graph there, we're going to see the doubling value is on the screen. So I can go in second trace, option 5, choose my 2 different curves, guess at the intersection, and I get a doubling value of about 55.8 years. So the solution t equals 55.8 is the doubling time. It's the d value. And if I wanted to write a slightly different equation that modeled exponential growth with doubling period, I could rewrite it as population equals 9.3, the initial value. Base is now 2, and the exponent, instead of being t, is now t over d, or t over 55.8. Okay, this concludes the video lesson. It's enough content here to be able to equip you to do the application problems. So we'll see you in class, and you have a chance to work on these problems together.